morning, everyone. I am Tran Van Bay1 coming from the Center of Sustainable Process Engineering at National University. Today I would like to talk about the CFD-PBE model of an air-kerosene bubble column under high pressure. This is containing the introduction, geometry and meshing, governance equations, population balance model, physical properties and battery condition, safety results and conclusion. As you know that nowadays the development of petroleum industry provide very important product for the other industry like gasoline, diesel, kerosene or gasoline. However, this development also enhance the amount of heavy oils we have a little application. So those products should be converted into the other useful product through the hydrocracking process. And due to that, we have many reactors, but the ceramic column is a typical reactor. And normally, the ceramic column works at high pressure and temperature to reduce the liquid viscosity of heavy oils and enhance the dissolved hydrogen in the liquid. So it's very hard and expensive to do the experiment for that system. And so to study the hydrodynamic ceramic column reactor, we firstly do the experiment for the air-kerosene system, which has which has a similar physical property to the heavy oils, and then we do the CFD simulation to predict the other unknown hydrodynamic parameters. This is the geometry, and we see the virus column with uniform gas splitter. The hexahydromestic used. Now I would like to talk about the mathematical model for the air-kerosene system, bubble system. This and I showed the gas liquid parameter model, including the continuity equation for the gas phase, the turbulent equations for the mixture phase, the momentum equations for the both the gas and liquid phase with the drag force and anti-drag force, where the drag force is predominant. The drag force proposed to the drag coefficient, considering three effects. The first effect is the effect of a single bubble in the viscous region, the distorted region, and the tap region. The second effect is the pressure effect, and finally is the effect of the swarm bubble. And the natural force is a total of brake force caused by the uniform of bubbles, the lubrication force caused by the effect of liquid viscosity, and the turbulent dispersion force caused by the interaction between these bubbles, and the pressure mass force caused by the movement of the bubble inside the liquid flow. This slide shows the population balance model with the mass balance of each bubble class. In this model, we only consider the interaction between two bubbles with the birth and death by breakup and birth and death by collisions. And to calculate the breakup rate, we assume that firstly, one entity can interact with one bubble with a specific corrosion frequency, and if the kinetic energy of entity is larger than the bubble energy caused by the surface tension, one bubble will be break up into two smaller bubbles with the break rate like that, and then one bubble can interact with many entities if the entity size is smaller than the bubble size. It can be broken into two smaller bubbles with the break rate like that, and finally is the interaction between many bubbles and entity with the total break rate like that. And to estimate the collisions rate, we show that only two bubbles can touch together with a collision frequency, and if the interaction time is larger than the collision time, two bubbles can be collapsed into a big bubble with the total pressure rate like that. And to take into account for the effect of pressure, we add up the pressure crossing factor inside the pressure column. You can see right. This slide summarizes the calculation of the CFD-PBE model to account for the effect of bubbles on the turbulent liquid viscosity. We use the bubble-induced turbulence model. And this is the physical properties and particle condition. You can see right here. To solve the PBE, the population balance model, the number of bubble glass is set to 30 beans. The minimum and maximum bubble size are 10 micron and 15 millimeter, with the initial bubble size is 2 millimeter. Now I would like to show you some CFD results. This is the model validation. You can see right here that the total gas depth and specific error agree with our experimental data. However, the short-term mean diameter is under-predicted with our experimental data, and the trend of short-term mean diameter is between input threshold while the specific error is actually. And this is the hydrodynamics predicted by CFD-PBE model. You can see that the gas short-term mean diameter, specific error, they are unstable at the lower part of the column, while they tend to reach a constant at higher part. At the bubble size distribution, you can see that the bigger bubble size distribution is narrow high pressure. That means the smaller bubble will be increased with high pressure. And let's see some animation of gas depth and bubble size. You can see that the smaller bubble is correspond at high pressure. And to conclusion, I would like to conclude my presentation. The CFD-PBE model was confirmed with our economic data in terms of total gas depth and specific pressure drop, so it can be used to predict this hydrodynamic of the gas of color vector under high pressure. And this product is supported by CCP and INI. Thank you very much.